The National Electrical Code, or NEC, Article 502.21c2 addresses hazardous classified locations and requires that conductors entering such locations be terminated in an enclosure that prevents the passage of gases, vapors, or flames into the enclosed equipment. Further, 502.21c2 specifically prohibits the termination of cables at the bottom of the enclosure in these hazardous locations. Article 409.2d of the NEC, which covers industrial control panels, mandates that these panels be constructed to withstand vibration and be equipped with the means for proper connection of grounding conductors and connection to the equipment grounding terminal. It is important to note that the NEC does not explicitly dictate the exact location of cable entries or exits on an industrial control panel in general applications. The International Electrotechnical Commission, or IEC, provides additional guidance through its standards. IEC 60204.1, Section 5.5, 2.3, which pertains to the electrical equipment of machines, states that connection boxes, cable entry plates, or equipment for cable entry or exit should be situated in accessible locations. The positioning should ensure that connectors and cables do not experience undue mechanical stresses. IEC 61439.2 Section 8.2 3.3, which addresses low voltage switchgear and control gear assemblies, specifies that cable entries and exits should be located in a protected place, ideally on the sides of the assembly. Considering both NEC and IEC standards, while neither explicitly prohibits cable entry or exit points on the back, top, or bottom of an industrial control panel in most cases, industry best practices generally favor locating them on the sides of the enclosure. This practice promotes accessibility for maintenance and inspection. It also minimizes the mechanical stress on the cables, which can contribute to longer cable life and more reliable operation. When designing or installing industrial control panels, it is crucial to consider the specific requirements of the application and the environment in which the panel will be used. Factors such as the presence of hazardous materials, the level of vibration, and the need for easy access should all influence the placement of cable entry and exit points. In summary, while the NEC and IEC provide frameworks for safe and reliable industrial control panel design, they do not offer rigid rules regarding cable entry and exit locations except in hazardous locations. Best practices, driven by considerations of accessibility and mechanical stress reduction, generally recommend side placement for these points. Always consult the relevant codes and standards for the specific application to ensure compliance and optimal performance. Article 502 of the National Electrical Code, or NEC, specifically addresses hazardous classified locations. Within this article, Section 502.21c2 details the requirement that conductors entering a hazardous classified location must terminate within an enclosure. This enclosure is designed to prevent the passage of any gases, vapors, or flames into the enclosed equipment, thus ensuring safety in potentially explosive environments. Furthermore, NEC Article 502.21c2 imposes a prohibition on terminating cables at the bottom of enclosures within these hazardous classified locations. This rule is in place to mitigate the risk of accumulating heavier than air hazardous substances that may be present near the floor. Switching focus to Article 409 of the NEC, we find guidelines related to industrial control panels. Section 409.2d mandates that these panels possess the structural integrity to withstand vibration, a common condition in industrial settings. In addition, the panels must be equipped with reliable means for connecting grounding conductors and establishing a connection to the equipment grounding terminal. These grounding provisions are crucial for personnel safety and equipment protection. Significantly, the NEC, while providing the above stipulations, does not explicitly define or restrict the precise locations for cable entries and exits on industrial control panels, except for the prohibition of bottom cable terminations in hazardous locations. This implies a degree of flexibility, provided that other relevant safety and performance criteria are met. Now let us turn to the International Electrotechnical Commission, or IEC. IEC 60200-1 serves as a standard for the electrical equipment of machines. Within this standard, Section 5.5.2.3 specifies that items like connection boxes, cable entry plates, and other equipment intended for cable entry or exit should be situated in readily accessible locations. The standard further dictates that their positioning must prevent connectors and the cables themselves from experiencing any mechanical stresses. This emphasis on accessibility and stress reduction aims to enhance maintainability and prolong the operational life of the electrical connections. IEC 61439-2 addresses low-voltage switchgear and control gear assemblies. In Section 8.2.3.3, this standard stipulates that cable entries and cable exit should be located in a protected area, suggesting the sides of the assembly as a suitable location. The rationale here is to offer physical protection to the cables and their connections, thereby minimizing the likelihood of damage from external factors. In drawing a conclusion based on the information presented from both the NEC and IEC standards, it becomes clear that neither organization explicitly forbids the placement of cable entry or exit points on the back, top, or bottom surfaces of an industrial control panel. However, there is an exception to this generality, which is the NEC prohibition against bottom terminations in hazardous locations. Despite the absence of firm restrictions, it is a generally accepted best practice within the industry to favor locating these entry and exit points on the sides of the enclosure. This preference stems from multiple considerations. Firstly, side placement enhances accessibility for technicians during installation, maintenance, and troubleshooting activities. Secondly, it minimizes the potential for mechanical stress on the cables, which, if left unaddressed, could lead to premature cable failure and associated operational disruptions. When making decisions about cable entry and exit points on industrial control panels, it is important to consider several key factors. These factors include the specific application for which the panel is designed, the environmental conditions in which it will operate, and the relevant safety regulations and industry best practices. By carefully weighing these considerations, designers and installers can optimize the panel's performance, reliability, and safety. To summarize, the NEC and IEC guidelines provide a framework for safe and effective industrial control panel design, but they do not typically impose strict rules on cable entry and exit locations, other than the prohibition of bottom terminations in hazardous locations. Adhering to industry best practices, which emphasize accessibility and stress reduction, usually leads to the recommendation of side placement for these entry and exit points. As always, consulting the applicable codes, standards, and project specifications is essential to ensure compliance and optimal results. Consider the physical constraints within the enclosure. Sufficient space should be allocated around the entry points to allow for cable bending radii and termination hardware. Overcrowding can lead to cable damage, difficulty in maintenance, and potential safety hazards. Choice of cable glands and connectors is also critical. They should provide adequate strain relief, environmental protection, and compliance with applicable codes and standards. Incorrectly selected or installed glands and connectors can compromise the integrity of the electrical system. Proper grounding and bonding are paramount for safety and electromagnetic compatibility. The grounding conductor should be securely connected to a designated grounding busbar within the enclosure, and all metallic components should be bonded together to minimize the risk of electrical shock and interference. The routing of cables within the enclosure should be carefully planned to avoid sharp bends, contact with sharp edges, and interference with other components. Cable ties, clamps, and other support mechanisms should be used to secure the cables and maintain a neat and organized layout. Consider the potential for future expansion or modifications. Leaving spare capacity for additional cables and components can save time and money in the long run. The design should also allow for easy access to all components for maintenance and troubleshooting. The environmental conditions in which the control panel will operate should be taken into account when selecting materials and components. Factors such as temperature, humidity, dust, and corrosive substances can affect the performance and lifespan of the electrical system. Regularly inspect and maintain the control panel to ensure that all connections are tight, cables are in good condition, and components are functioning properly. A preventive maintenance program can help identify and address potential problems before they lead to equipment failure. Consider the use of cable management systems such as cable trays, ducts, and flexible conduits to organize and protect the cables entering and exiting the control panel. These systems can improve the appearance of the installation, reduce the risk of cable damage, and facilitate maintenance and troubleshooting. The use of proper labeling and documentation is essential for identifying cables, components, and terminal blocks. Clear and accurate labeling can save time and reduce the risk of errors during installation, maintenance, and troubleshooting. The documentation should include wiring diagrams, component lists, and other relevant information. Consider the use of surge protection devices to protect sensitive electronic equipment from voltage spikes and transients. Surge protection devices can help prevent damage to components and reduce the risk of downtime. Ensure that all personnel working on or near the control panel are properly trained and qualified. Electrical work should only be performed by qualified electricians who are familiar with the applicable codes and standards. Proper lockout/tagout procedures should be followed to prevent accidental energization of the equipment during maintenance or repair. Consider the use of arc flash protection to protect personnel from the hazards of arc flash events. Arc flash protection can include the use of personal protective equipment, arc flash relays, and current limiting devices. The design of the control panel should comply with all applicable codes and standards, including the National Electrical Code, the International Electrotechnical Commission standards, and any local regulations. Compliance with these codes and standards is essential for ensuring the safety and reliability of the electrical system. In hazardous locations, the control panel should be designed and installed in accordance with the requirements of Article 500 through 505 of the National Electrical Code. These requirements address the specific hazards associated with flammable gases, vapors, and dusts. The control panel should be located in an area that is easily accessible for maintenance and troubleshooting. The area should be well lit and free from obstructions. The control panel should be protected from physical damage, such as impact from forklifts or other equipment. The control panel should be properly ventilated to prevent overheating. The ventilation system should be designed to remove heat generated by the components inside the panel. The control panel should be equipped with a disconnecting means that allows the power to be shut off in case of an emergency. The disconnecting means should be clearly labeled and easily accessible. The control panel should be equipped with overcurrent protection devices, such as fuses or circuit breakers, to protect the electrical system from damage caused by overloads or short circuits. The overcurrent protection devices should be sized appropriately for the loads they are protecting. The control panel should be equipped with a ground fault protection system to protect personnel from electrical shock. The ground fault protection system should be designed to detect and interrupt ground faults. The control panel should be equipped with a surge arrestor to protect sensitive electronic equipment from voltage spikes and transients. The surge arrestor should be sized appropriately for the expected surge levels. The control panel should be equipped with a lightning arrestor to protect the electrical system from damage caused by lightning strikes. The lightning arrestor should be grounded to a grounding electrode system that meets the requirements of the National Electrical Code. The control panel should be inspected regularly to ensure that all components are in good working order and that the panel is properly grounded. Any damaged or worn component should be replaced immediately. The control panel should be cleaned regularly to remove dust and debris. Dust and debris can cause overheating and equipment failure. The control panel should be kept dry to prevent corrosion. Corrosion can damage the electrical components and reduce their lifespan. The control panel should be protected from insects and rodents. Insects and rodents can damage the wiring and components inside the panel. The control panel should be locked to prevent unauthorized access. Unauthorized access can lead to tampering with the electrical system and create a safety hazard. The control panel should be labeled with warning signs to alert personnel to the potential hazards. The warning signs should be clearly visible and legible. The control panel should be located in a secure area to prevent theft or vandalism. Theft or vandalism can disrupt the operation of the electrical system and create a safety hazard. The control panel should be designed to be easily expandable to accommodate future needs. The design should allow for the addition of new components and wiring without requiring major modifications to the existing panel. The control panel should be designed to be easily maintained. The design should allow for easy access to all components for maintenance and troubleshooting. The control panel should be designed to be energy efficient. The design should minimize energy consumption and reduce the costs of operation. The control panel should be designed to be environmentally friendly. The design should minimize the impact on the environment and promote sustainability. In addition to these general considerations, there are also some specific considerations that apply to control panels used in hazardous locations. These considerations include the use of explosion-proof enclosures, intrinsically safe circuits, and other measures to prevent explosions. The explosion-proof enclosures must be rated appropriately for the hazardous location in which they are installed. Intrinsically safe circuits must be designed to limit the amount of energy that can be released in the event of a fault. Other measures to prevent explosions include the use of purged enclosures, pressurized enclosures, and oil-filled enclosures. The purged enclosures are filled with a clean, dry gas to prevent the accumulation of flammable gases or vapors. The pressurized enclosures are pressurized with a clean, dry gas to prevent the ingress of flammable gases or vapors. The oil-filled enclosures are filled with oil to prevent the ignition of flammable gases or vapors. The selection of the appropriate type of explosion protection depends on the specific hazards present in the hazardous location. The NEC provides detailed requirements for the design and installation of electrical equipment in hazardous locations. These requirements must be followed to ensure the safety of personnel and equipment.